So our third and last presenter for this session is Justin Porter from Rice University. His field is mechanical engineering, and he's done practicums at Lawrence Livermore National Laboratory as well as the National Renewable Energy Laboratory. And today he'll be presenting on prediction and modeling of nonlinear vibration in bolted connections.
Thank you for the introduction, and then this is work that I did with my PhD advisor at Rice, Dr. Matthew Brake. So joints are everywhere, and these are a number of photos I've taken over my time in grad school of just random things being bolted together that I've come across. And then I'm also interested in vibration. So on the bottom here, you can see my printer is trying to print something, and it's shaking my internet modem back and forth. So these are the type of concepts I'm interested in, but these aren't necessarily of great engineering importance. So really more interested in applications to aerospace, such as jet engines and power generation systems, where these have multiple bolted connections and then also exhibit vibration behavior that's important for determining the lifespan of these structures. So annually, an estimated billions of dollars is spent on vibration testing, and this can be attributed to a lack of an ability to predict vibration behavior before building a prototype of the structure. And jointed connections are one source of uncertainty in these predictions. This also results in an estimated tens of millions of dollars in fuel, with a calculation of 3,000 gallons of fuel per kilogram of mass on commercial airliners per day across the entire US commercial fleet. So there's quite significant fuel and monetary concerns with understanding vibration behavior, and if you can understand it early in the design process, you can improve designs, reduce weight, and improve efficiency. So going on to the backgrounds of what I mean by vibration and how I'm looking at it. So here on the x-axis is the frequency of some response, and you can think of this just as being related to the engine RPM, and the y-axis is some measure of the response amplitude. And larger amplitudes are undesirable because they can lead to failure and damage to the system. And there's going to be some resonant frequency where you get the largest amplitude. So for linear systems, if you go to a higher forcing magnitude over the same frequency regime, the response curve just moves straight up. This is very convenient, very easy to calculate. It's proportional. But I'm interested in nonlinear vibration due to bolted connections. So now instead, I have this greenish curve that is shifted over. So this is a shift over in frequency, but it's also a change in amplitude. So the change in amplitude can be beneficial, but you need to know where this new frequency that it's most likely to fail is. So this is attributed to friction for bolted connections. So as the system is initially stuck, but then starts slipping, it loses stiffness. So that's this change in frequency. But this slipping also dissipates energy. That changes the amplitude of the response. So I want to understand both of these changes in the response. So to calculate this, I'm going to look at a nonlinear eigenvalue problem, which is extending a linear eigenvalue problem. So from linear algebra, you can solve this generalized linear eigenvalue problem, and that gives you just this frequency for the linear system of this peak response. And this is much easier than calculating this full response curve. You can actually recover the response curve from this eigenvalue solution. For the nonlinear eigenvalue problem, instead of it just being a linear algebra problem, now I'm solving something that looks like this, where I say the response subject to some ODE and doing time integration returns to the same response after some time period, capital T. And this time period, capital T, you can think of as being related to this nonlinear eigenvalue, and that's going to track how this frequency evolves with amplitude. So that's what I'll be showing later with some of the results. So step one for this modeling is that friction is fun, or F equals mu n. So if you took an introductory physics class at some point, you probably would have seen an example like this. And what you would learn in that physics class is that this block will start sliding down this ramp when the force pushing it down the ramp is equal to some constant friction coefficient times the normal force. So this is very simple, seems straightforward for what friction is. Except I'm going to look at friction in a bolted connection. Spoiler alert, it's not nearly that simple. So this is the Brake-Rice beam, which is an international benchmark that I'm modeling to understand the frictional responses. So friction is more than fun. So I started out with a scan of the interface. So here it's on a 23 micron grid. So there's a lot of data here. And first, I level and filter the data to get a mesoscale topology. So nominally, this is just two perfectly flat interfaces coming into contact if you look at the CAD model. In reality, there's actually this 100 micron gap at the center of the interface. And that's just due to machining error. And it doesn't sound like a big deal, but it turns out to be a big deal in the models. And then I also look at individual peaks. So the surface, in addition to this arch shape in the gap, it also has some waviness and local maxima. So I fit those local maxima as asperities. And these are just idealized as ellipsoids or spheres that are the local peaks. And this is what's going to be coming into contact. So this is where I'm going to apply the physics. And these have some statistical distribution of the initial distances between these because all points of the interface don't come into contact at the same time. And this is in addition to the deterministic mesoscale topology. So to calculate the contact between those points, I'll just quickly go over some of this. In the normal direction, these spheres or ellipsoids initially have a nonlinear relationship for elastically coming into contact. Then they plastically deform, and there's permanent deformation. And then since there's permanent deformation, when they start separating again, they're following a different curve. So I need to consider all three of those. In the tangential direction, these two spheres or ellipsoids pressed together will initially act as some linear spring. But this linear spring varies depending on how much they're pressed together in the normal direction. And then I end up apply this proportional friction limit at every single set of these asperities. But these also have the statistical distribution, so they all have different normal pressures and are going to slip at different times. So now going into just some results from this first friction model. So the first set of results here with the lowest frequency, with the stars, is when I emit that mesoscale topology, so that 100 micron gap at the center of the interface. And here I'm getting a much lower experiment than this solid black line, which are the experimental results. So it's very important to capture that machining error in the model. Otherwise, you can't predict the frequency response of the system. This green dotted line in the middle is if I exclude the permanent deformation and just have elastic contact between the asperities. So by including, though, that initial gap, it is getting better, but there's still some error. And then finally, the top line with the triangles and the dashed line is the best predictions of the model, including the permanent deformation of these contact points and this initial gap of 100 microns at the center of the interface. And then, so this is shifting, or how the peak shifts along the x-axis, and then measuring energy dissipation on the bottom with the damping. You can see that all of these curves are doing a good job of qualitatively capturing this smooth increase in damping behavior. So compared to the literature, the previous benchmark for predicting frequencies of jointed structures was about 25% error in stiffness. And with my work, I was able to reduce that prediction error to about 3% error for the low amplitude frequencies. And with damping, I'm better able to capture this smooth behavior. So now I was doing friction, just kind of plugging things into the model, started getting a little bit bored with that. And with CSGF funding, I had the opportunity to go and do something completely different and go focus more on nonlinear vibration. So started going down this path and turned and went back. Didn't know exactly what I was doing, so I was lost for probably 6 months to a year figuring out what exact problem I was going to solve. And there I did a practicum at Lawrence Livermore National Labs, and then I started narrowing down. So previously, I told this nice story of linear vibration, the peak is constant. I'm going to generalize to nonlinear, now the peak's going to shift, but it still looks kind of similar. It's just one value that was a constant is now amplitude dependent. But now I'm going to look at this nonlinear phenomena where all of a sudden there's two peaks. So what is going on here? This is attributed to a superharmonic resonance, which is a large response at an integer multiple of the forcing frequency. So if you think of a piano, so you hit one key and you expect just to get out the note for the key that you're hitting. And this is what a linear vibration system does. But now for this superharmonic resonance that can sometimes occur in nonlinear systems, you also get a note out at 3 times that frequency, or a different multiple, even though you didn't hit that note on the piano. So this is the type of responses that I want to be able to capture and better understand with the modeling. So from here, I developed an approach to track where these superharmonic resonances are occurring and then also applied reduced order modeling using that tracking approach. So here, the solid black and gray lines are the reference solutions, and the previous state of the art is this dashed green line that is completely missing this double peak behavior. So in the first paper, I developed this orange line, which tracks where this local minima is. And in the second paper on the topic, I developed this new dashed line on the right that is a reduced order model that better captures this double peak behavior. Now, this reduced order model is significantly faster than the reference solution because you just calculate this orange curve and a couple other summary curves, and then you can use this reduced order model to calculate responses at multiple amplitude levels rather than using the reference solution, which is more computationally intensive. So with my time in CSGF, also had an opportunity to go to a number of things and accumulate a number of lessons to improve my software engineering. So I attended 2 supercomputing conferences in person, and then I also had a chance to do a second practicum at the National Renewable Energy Lab. So from these, learned about unit testing, which from a mechanical engineering background isn't really covered in our undergrad or even graduate courses. So I have about 200 unit tests on my final code. And that's stuff I picked up from the Lawrence Livermore practicum and going to supercomputing. From the NREL practicum, I learned about YAML input decks, which are very easy to write by hand and then import into Python as a dictionary, and really helped me efficiently parameterize studies for my final projects of my PhD. And then also at supercomputing this past year, learned about automatic conversion from docstring comments to HTML, so I've been implementing that for my code as well. And here's all of the photos from these different things that CSGF gave me the opportunity to attend. So now I have this nice reduced order modeling, but this is CSGF, so I need to apply it to a large model. So to finish out and get out of the wilderness, I'm going to apply it to a jointed structure. And here, just a quick side note, I use JAX, which allows for automatic differentiation in Python. So with that initial friction modeling, I would joke with my advisor that maybe I can implement new physics in a few hours, but it's going to take me a few weeks to calculate the derivatives so I can actually put it into the solver so I can tell you what it actually does. So with automatic differentiation, if you're in that situation with your research, I was just able to completely eliminate implementing those derivatives, and it's so much faster and can get more done with scientific computing. So for this, I'm looking at the half-break Royce beam, which is just a modification of the previous jointed structure I showed. And here you see my experimental setup from the experiments I ran. And this shows a 7-to-1 superharmonic resonance, where if you excite it near the first mode, which is about 82 hertz, you also get a large response at 7 times that forcing frequency, or about 574 notes. So on a piano, this looks like you're hitting this first note with the electromagnetic shaker. And yes, I did look up the frequency of these keys on the piano. And you get this vibration shape at that frequency. Then at 7 times that frequency, or approximately this note on the piano, you get this additional vibration shape, even though the shaker is only exciting this first frequency. So just looking quickly at some results here, I have experiments that are off to this side with the dots and the X's, and then the reference model and the solid black and gray curves, and the reduced order model and the dashed line. So these experiments are conducted at constant amplitude for the output of that first harmonic. So the input force is varied. So that's why this is going to a local minima. And you can see that the models are doing a good job qualitatively capturing the experimental results with some uncertainty in the experiments. And then the reference solution here is very computationally intensive. These ran from around maybe 4 to 10 hours on one node of the cluster. So I have significant faceting, and at the corners, it is matching this reduced order model. But with the reduced order model, it's much faster, so I can get higher resolution and actually resolve where this local minima is occurring. And then I also have this response at 7 times the forcing frequency that I want to capture. So using my tracking approach, again, I can do a reduced order model that's doing a good job of matching these reference solutions. And qualitatively, these are very similar to the experimental results, again, with some experimental error, but that's to be expected. So overall, this reduced order model provides insights into the phenomena of interest in what is causing these responses at a multiple of the forcing frequency. Construction of the model, or the reduced order model, was 4 times faster than the reference solution. So this is running the tracking approach rather than calculating the reference solution at multiple amplitude levels. And then once the reduced order model is constructed, evaluating it for new amplitude levels is essentially free, with a speed up of 780,000 times faster. And that's because once it's constructed, you don't need to solve any nonlinear equations to evaluate the reduced order model at new amplitude levels. So with that, going to the conclusions from what I've taken away from my time at CSGF and these projects. So friction is more than fun, or more than just F equals mu n. And with my new model, I'm able to predict natural frequencies with less than 3% error. And then for the reduced order model, it again provides insights into phenomena and significant computational benefits. And then from CSGF, I've accumulated a number of lessons. It was very useful for me being able to get lost in the wilderness and learn how to get out with research and set my own project directions and goals. And then also useful things, automatic differentiation, YAML input decks, unit testing, and this HTML documentation conversion. And one final time, I would like to acknowledge the Department of Energy's Computational Science Graduate Fellowship for funding all of this, and just very appreciative of the program. And with that, thank you, and I'd be happy to take any questions. And here's my lab group at Rice.